All right, okay, so, well, today is lecture 7. So, today's topic is about the first lecture on classical statistics. This is okay. This is the topic that we're going to start. Actually, as I mentioned earlier, that actually we still have one topic to cover in the thermodynamics context about real gas. But to understand that context, we need some ingredient or some tools from statistical mechanics. Then I decided to start to teach you this first, and then we come back to that topic later. Okay? So, well, I just would like to emphasize this one again. So the effects that we're going to consider in this context is still classical, no quantum effect at all. So, okay. Okay, so the first thing that you have to understand about concept of ensemble, okay, this is, have you ever heard about the word ensemble? Can you give me like a short explanation or any words or any definition that you have in your mind about this? What is an ensemble? Right. Well, kind of yet that, but in general, actually, it means a collection of things. Actually, that would be a very simple thing to say, but in this context, it's going to be like a collection of states, right, that we consider, right, that is the thing. Okay, so we start again with a system of a classical gas. Okay, right here with n particle. Okay, so well, this is maybe also include interaction. Okay, right. But in the previous class we considered the ideal gas, which is actually we exclude all the interaction, right? But suppose that we also include interaction into the system, but the gas is still classical, no quantum effects and there is n particle. There are n particles in your system. All right. Okay. So suppose that we have a box of this classical gas. Okay. This is a box of classical gas. So we have a set of I would say a set of generalized coordinates, right? okay, which is I going to define to be as this Q. Suppose that, okay, you know what it means by this word generalized coordinate, right? Do you know what it means, right? Okay, okay, and a set of conjugate momentum, okay, which is actually P. Okay, this one. And totally here we have 3n. Yeah, I would put this number. Okay. Also here we also have 3n. Okay. So in total, we have 6n number of variables to deal with. Okay. Okay. So this means that we have 6n dimensional manifold. I'm not going to give you a precise definition of a manifold because it's not relevant in this context, but I suppose that to make it simple, manifold is kind of generalized of the surface to the higher dimension. Okay, that is a very easy way to explain. But well, as I mentioned, there is some other condition that you have to consider. Actually, the space that you consider to be manifold or not. All right. Okay. We call this manifold. There are two names actually. The first one is called cotangent bundle. All right, and the second name, as you know, is called phase space. Okay. Right. But in this context, I'm going to keep using this word phase space because we are not in the context of classical dynamics then or geometrical mechanics, then we are not going to talk about geometrical language, then just ignore cotangent bundle, but just let you know that actually they are the same. Okay. And so I'm going to put this symbol to represent the phase space, right? Okay. And to draw in this context, so we're going to draw. So this is like okay. This 2D diagram represents 6n dimensional space, and each point here, this contains 6n variable, right? Which is PQ. Okay. Let me put this trial bracket. Okay. And in P you have 3n, And in Q, you have another 3n. Then totally you have 6n. Okay? All right. And suppose that this is going to be your initial point. All right. You have also another point, actually the final point, right? And you have, of course, this gives you a trajectory, all right, of the whole system. What I mean by the whole system is means that actually not only single particle, but all of them together. You can represent the whole state of this whole bunch of particle in just one point on this space. Okay? Right. Okay. Any question up to here? Okay. So then it means that I can say that actually it would be the initial state at time 0, and it would be the final state at later time t, where t greater than 0 here. Okay. So each point on this phase space, right, represent a state of the microscopic system P and Q. Okay. What I mean by microscopic system is, I mean that actually the system, this kind of the classical gas system, right? Okay, and the time evolution of the system is given by the trajectory. Okay, right. Well, this is kind of subject to also the initial condition, right? If you start at some other point, you will get different trajectory. Yes, of course. What I mean, this is what I mean by subject to the initial condition. Okay. All right. Up to this point, any question? No? Okay, good. Okay, so next, an observer of the system. Suppose I use this kind of fancy O here. is an arbitrary function of P and Q such that this, okay, time average value starting at t equal to 0 with the initial state here is defined okay, right, and this somehow this is a macroscopic observer, I think this is a macroscopic thing. Like if you want to compute the pressure of your gas system, right, or that kind of thing, that we, for example. So mathematically, this kind of function, okay, this note here. This kind of function that actually belong to a set of function that define on phase space. You can have a lot of function that actually define on this phase space. Right. This is representing a set of function defined on phase space. All right. Then it means that if you have phase space here, right, and you have this to be your real line, this point PQ, right, this operator, you can think this is as a map, right, because after you put, if you look at this, after you put P and Q into this function, you have to get you get a number, right? Yeah, that is the reason why is you can think this is a map, right, to on the real line. Yeah, is that clear? Okay, good. And again, right, okay. So let me emphasize you again the reason why I put this bit here. I would like to say that actually again this is subject to initial condition, right? Okay. Okay, so as time pass, the trajectory, the dynamic of the system, right? The phase space. Okay. I mean, you should have as this time t. Suppose that actually this is your initial point. So this is your trajectory, right? And then this is at time t0, right? And then this should be at time t. And so once this is at time 0, at time t, and then this is t pound, which is actually, so your trajectory will get more complex and complex, right? That is the reason why I use this word wide. It means go spreading to this space. I need to extend a little bit. Okay, this T0. I hope that I still keep thing in the same. Okay. Okay, this style thing. So your trajectory, you get kind of more and more complex, right? But keep in mind that actually, if you start with different initial conditions, you will get different kind of pattern of your trajectory. Okay. So if the motion Okay, so this is the feature that we expect. Let me explain. If you leave your system long enough by, well, mathematically it means that you take time to be infinity. So the average of any quantity that you consider here should be somehow get to some certain value, and that some certain value is mean that is a constant somehow. It's a called equilibrium value or constant. It means that at that point is doesn't depend on time anymore, right? That is the thing. It should be kind of that what the feature that we expect. So how now come to the question. So what would the phase space trajectory look like if the system approach dynamic equilibrium. Okay, so yeah, that is the question. So what is your trajectory will look like if like this? If you leave it long enough, what kind of pattern of trajectory will be look like on this space here? Okay. So and here is an answer. So one can say that the frequency with which different neighborhood of the phase space visit converge to a finite value. So we could define this. I mean, this would be represent the frequency, right, or the density. Yeah, that is the thing at each point in phase space. Well, this is a bit abstract, of course. Okay, I will try to draw you a picture to see what I mean by this message, right? Suppose that you have phase space here. So this is suppose a point, right? Okay, so it's I mean that it might be area around this point, right? And the trajectory that actually passing through this and this, well, you might expect that would be a lot, right, of them that passing through this point would be on the average the same with this point, the yellow point here. So you might expect not get close to the point, just passing by very close to. Okay, that is the thing. Yeah. Well, approximately the same. Okay, you see, so now you get the idea about this sentence, right? Okay. All right. Then for very large n, it is very difficult, right, to determine a particular position of each particle, right? Okay. However, what we are actually interested is the macroscopic quantity, right? I mean, this object actually belong, right? What we are interested in is the quantity of this observable, not really what really going on inside the box, really, right? Because we cannot, in principle, we can keep track, but it's going to be very, very difficult to do that, and it's not useful in practice, right? So like energy or the volume or the pressure, like this is a thing that comes from the thermodynamics, right? Context, right? Because in the thermodynamics context, we need to compute all these quantities, right? And which it is a consequence of a large number of microscopic microstate, actually. What I mean by microstate is the point on this space, right? Microstate. What I mean is this kind of point on this space, right? large number point in phase space. And or we call our ensemble of system is a set of all possible micro state. Okay. Yeah, it's a definition of ensemble in this context, right? It's a set of all possible micro state. Okay, that is the definition of this. Yeah, of course, this is a this is a classical ensemble, right? Yeah. Okay. Any question up to this point? Mm-hmm. Yep.
The number has to be a set.
Yeah, a set.
So it's just not one possible micro state. Is that?
Well, you can say that actually your ensemble has only one. Yeah, that's fine. But the thing is that you know that actually this is a kind of statistical mechanics. There is some kind of information that we cannot access, right? That kind of ignorance. That kind of ignorance gives us some kind of uncertainty, but not quantum uncertainty. This is a totally classical uncertainty. Then give rise to somehow probability, somehow, right? And then that is the reason why we need to compute all this kind of average here, because there is some information that we cannot access. I mean, what that kind of information is this. I mean, the particular position of each particle. No, you cannot. In principle, you can, but in practice, it's very, very difficult, as I mentioned here. That is the reason why it gives rise to this kind of uncertainty, classical uncertainty. And then that is the reason why you have to compute kind of average of the thing. Cannot. Okay, and then of course after that it's going to give rise to this kind of macroscopic quantities, right? But well, thing is that if your system contains very few particles, there will be kind of weird thing happen. I'm going to explain to you later. Suppose that in the box you have only one particle, and then let's see what happened later. Okay, and then you will see that is the reason why we need kind of very large number here. Right? Because it's somehow well, let's put in this way. Okay, so note here. Okay. Think about large number of particle. Okay, so suppose that here we have a box. I'm going to point you out here at the moment, or the feature that we're going to have, but we're going to deal with the computation later. The feature that you could have, suppose that you have a bunch of particle that is that times 0 here, a bunch of particle, n particle, Okay, so for later term, which is actually greater than 0, what do you expect to have in the box? What kind of configuration of the gas that you could expect? So the gas going to spread out and contain the whole volume, I mean whole space of the box, right? Yeah, that's what you get, you normally get, right? You get that actually. This is what you get. Yeah. So there is no way that your gas, I mean, at later time T pump, which is actually okay. T pump, which is actually greater than T greater than 0. So you have a box again. Sorry, I have no space. My box is a bit distorted a little bit. So, well, you will not have this kind of situation that at some later time T, this whole bunch of the gas will collapse, and then get into this corner again. No, this is not happen. Not happen. This is not happening. Okay, but the thing is that is if you have only a single particle, you have only a single particle here, suppose at time 0, and later it's moving out, right, on from the corner to be somewhere in the box, yeah, at time greater than 0, right? And then, well, when you leave it for some time, it might be that happen that your particle can get back to this point again. This is get back to the original point. This is kind of different thing that you should have in the case of you have a very large number of particles and a very few number of particles. Especially in this case, you have only a single particle in the box. You're going to have this kind of different feature, and I'm going to explain this in detail later. Okay? All right, then move on. So now, where are we? Actually, okay. Okay, let a state of the system be specified by a set of this coordinate and we postulate that the probability for the system to be in a neighborhood of the state Q is this one. Okay, this is going to define a plot, all right? Okay, as I mentioned, if you think this is a density, right? Yeah, this would be the plot density, and this would give you a number of point, right? The content in an element volume. What I mean by element volume is this one. Okay, this would be the element volume, but you have to understand it's going to be like the volume in the hyperspace, right? Because we are now dealing with the 6n dimensional space, right? Okay. Okay, now okay, so I explained to you the reason why we get, the reason why we have to deal with the probability, right? I explained to you earlier, and then now when we're talking about probability, then you know that there must be a constraint, right? Like a normalization that the total plot you have it has to be 1, right? That's kind of thing. Right? But we're going to talk about that now. Now, yes. So it gives the function of the system in the ensemble that are in the state PQ. Okay. Keeping with usual plot notion, right? So you need to get to have this kind of condition h to the n. So, well, I put this factor to make sure that you can normalize it. Okay. So this is going to be normalized, normalizing factor, right? Okay. Yeah, right. So then with this kind of notion of this density, we could compute the average of the macroscopic quantity like a fancy O, but with respect to the ensemble, because this is the kind of density of the point in the area that we in the space that you consider, right? Then we can use this kind of thing to compute the expectation value. All right. Okay. So now we have what we call the ensemble average of this quantity, our fancy O, is defined as okay. This is going to be the definition of average of this quantity with respect to the ensemble. Okay. Any question up to here? Not yet, right? Okay, good, very good. You understand everything? Okay. Okay, so now okay, yep.
Is this not the right
Yeah, it's probably be the same. I'm not sure that what you put there is a product.
yes for that?
Right. If it's a product, it's the same.
Yes.
Yeah. No, if that is a waste product, it's not the same.
Not the same.
Yeah, because yeah, it's just like for this one, it's you get P1, P2, P3, and then you get in the Pn.
Yeah, this, I know that, but I just not clear why we not use the base product in this phase space.
Well, actually, we can use that actually because the phase space equipped with the symplectic structure, you need that actually. But as I mentioned, we don't need that kind of language. In this context, then we are not going to use that kind of waste product. But actually, if we talking about symplectic structure of the cotangent bundle or the phase space, then of course that we need then yeah. But for this context, we don't consider that kind of property seriously. Actually, but you have to understand that actually there is a kind of symplectic structure equipped with on this space. All right. Okay. All right. So now we have okay. We have what we call Birkhoff theorem, which what is that? Okay. Is that interesting? It's like some invincible person sitting on the couch, And then the motion okay, if the motion is contained in some particular bounded domain, okay, so for many inertial condition, that exists on some this is my such that, this is my shorthand for such that, okay? Okay. The time average value of the observer O equal to an ensemble average. Okay. And if you have this kind of condition, you know that which is it is known as the ergodic hypothesis. Okay. But again, I'm not going to talk much about this kind of ergodic hypothesis, but I might give you as a homework to start to explore more about this hypothesis, what this is about. Okay, I'm going to decide this as a homework. Okay. So the point that let me put, if you look at this message again, you will see this in many initial conditions. What does it mean by this message? It means that this doesn't depend, right, on initial condition, right? Whatever initial condition is, you will get exactly the same average, the time average, right? That is the thing, okay? As if you leave the time long enough, right? So again, what does it mean by having this condition here? Let me draw you a picture. I will try to make a cartoon for you to make sure that actually you get the point, because this is kind of a bit abstract, right? So here on this side is the time average. On this side is the ensemble average. I draw you a picture of the ensemble average, right? Okay. So let's do it again. So suppose this is the point, and then there is a neighborhood right here. So you will get a trajectory that get very close, very close, very close to this point, and the same with this one. Okay, you will get this is somehow right. This is what you're going to have on this. I mean, right. And for this PQ here, it means that suppose there is a point here. This is the point. Okay, that we consider. And you might start with this as an initial point. Then let's put a yellow point as a point that we consider. So it means that again, so you will get some kind of neighborhood area around this point. If you start with this initial point, and then you leave your system flow, so it means that it's going to pass, more, this kind of thing, right? If you change the initial point to be this one, I2, I suppose this is to be I1, and you leave your system again, you will get exactly the same, okay? And if you start with the I3 here, if you leave your system, and then you will get actually the part that passing through the point, which is actually the same here, okay? Is that clear? Okay. This is kind of a very cartoon thing that I try to make sure that you get to understand to that. Okay. Can I take like 2-minute break? I need to drink water. Okay. Let me take 2-minute break and then come back. Okay, let's continue. So far I explained things to you on the phase space, right? And so, well, we know that actually when we're talking about phase space, we have to deal with the Hamiltonian, right? Okay. Suppose that the Hamiltonian of the system is given by so the first term is going to be the kinetic. So I treat that all the atom in the system have exactly the same mass for simplicity. And so you have a potential which actually might be the interaction, right, between each of the particle, and also it might be kind of a potential for each of them. All right, it's like in the harmonic well, something like that. Okay. So in principle, you could have this kind of Hamiltonian, but we are not going to specify this kind of interaction yet. Okay. Then you learn from the classical dynamics that on the phase space there is so here we consider the Liouville theorem. Have you ever heard about this Liouville theorem? What it's about? Can you give me a little bit idea about this theorem? Yeah, well, that's fine. Just give me your answer. That would be okay. No, not really. It is something about volume preserving. Yeah. Throughout the flow, right? Okay, let's see how it works. Okay, suppose we have this rho, okay, which is a function, a density, as a function of P and Q, right? We consider we look at the time derivative okay. So if you look at the time derivative of this function, I mean the rho, so the first term you're going to get this kind of partial derivative, right, in this case. And so you will get, of course, that you will get by doing the chain rule. Okay. Okay. It must be 0. Otherwise, what does it mean? If it's not equal to 0, what does it mean? Can you give me the answer?
Each has it's hard to say. It has a change on the generalized coordinates.
No. Well, yeah, you can of course you can change of the coordinate, but this is something to do with the density or the number of points that contain in your your area that you consider. It means that if it's 0, if its derivative with respect to time to be 0, it means that the number of points, right, is constant, right? So if it's not, then this is not constant. That's it. Simple as that. And then if it's constant, so it's going to be related to this volume preserving, right? I'm going to explain to you later with the cartoon picture again. All right. So suppose that we put this condition, we need we actually get this quantity. Okay, and so now we recall recalling the the Hamilton, yeah. Recalling the Hamilton equation, okay? Yeah. I believe that you knew this. Yeah, right. And you plug this to quantity into this equation. Right. So you will get that the time derivative of this row can be expressed as and the first term is Q dot is going to be this, and the second term Q dot Q. Okay, is it look familiar to you now? I mean the second term here. Yeah, of course. Is it nothing but the Poisson bracket? So you get a Poisson bracket of the Hamiltonian with the row. Okay, yes. So this is the equation that we have. Equal to 0, actually. So let me put here a statement for you. So the distribution function is constant. I mean, the distribution function is nothing but the row, right? It's constant. along the trajectory in the first place. So here is statement of that equation. Okay. So if you would like to draw a picture, you could, of course, this is P, this is Q, right? So if you start your system with this suppose this is like 6n object, okay? I mean, okay, that actually live in 6n dimensional object. And of course, there is the number of points that actually contain in this, in this volume, in this area that you okay. So the thing is that according to this equation, each point of this that actually live in this hyper object here, going to have its own trajectory to be here, suppose, okay? And this point, of course, is going to have their own trajectory to be here, okay? So it means that, so suppose that this is at 0, okay? And so this would be a new shape, all right? I know that actually the volume here is still the same. It means that so the number of points here still the same. It means that every single point that contained in this object will be moved to be in the new object here in later time t. Okay. Okay. I suppose I give you another trajectory here. Right. Hope you get. And so suppose that you have this row 0 here, and then this is row t, which is actually 0. Then you get that actually it must be the same, all right? And so if you could think this row can be defined by this volume per number of point somehow, right? Okay. Is going to be the same here. That actually this should I put the 0 here maybe? Yeah. Let me put in this t, okay, nt, and this is N0, and so it's going to be the same with this one. Okay, right. That this is what we have from this Liouville theorem. Okay. All right. So, any question up to here? Yeah, of course. It doesn't change with time. Even the shape of the area that you consider change, but the number of points still remain the same. Okay, it means that the ratio, is still the same somehow. Yeah. I mean, even the shape change, but this kind of the ratio is fixed, right? I mean, the volume of this object and the volume of this object is the same. It means that, so here, you could think that actually the flow that actually happen through this process, the flow, I hope you get my point, the flow is incompressible, right? It's like a fluid thing. If it compressed, if it can be compressed, it's not going to obey this kind of thing. Okay, this kind of this condition. Yeah. Okay, cool. So we now consider an isolated system with a fixed number of particles with volume V and an energy that actually varying between E and delta E. This is the variation of the energy, right? Is very small. So I give you a definition of the isolated system already, right? Then I'm not going to repeat it here. Okay. So on the phase space, again, you probably have, this might be the area that actually representing the energy E, right? Okay. And this dash boundary representing E plus delta E. Okay. So this called the energy shell. Right. Can you imagine that we have like you have a sphere, right, in 3D, but this is going to beyond into the hyperdimension, right? Okay. Are you okay? So now we consider at equilibrium, right? As well, you have to understand that the context that we're dealing with so far is the equilibrium thermodynamics, right? And that's the reason why we at equilibrium, right? No particular region of energy shell should play a special role or point in shell have the same statistical weight. Right. The microcanonical distribution. Okay, so here we have the first word, the microcanonical, right? Which is actually related to this kind of isolated system, the condition that we have here. Can be postulated to have so this could take the form okay, otherwise is 0. All right. I mean, so if it's in the shell, the density should be constant by and is proportional to this quantity, which is actually the volume. This going to be of the shell. Okay, defined as the volume of the shell. All right, and constant, and the whole term is constant. Okay. So this symbol, this omega could be represent the surface, right, area, right, of the energy shell, right. So if you think it's simple enough that you have a surface and multiply with the width, you get the volume, right? You have a surface, you multiply with this, the width, right? You get the volume. That is the thing. Okay, is that clear? And this, but this surface also depends, yeah, on the energy of the system, right? That is the thing. Okay. And so, of course, that this can be considered as a normalized station factor. All right. Okay. Because you need if you do the integration of this law, it has to satisfy the probability condition, right? Then you can use this kind of constant to make sure that you get the probability condition right here. And so if we, so now I define this thing as the volume of the phase space, right? The volume that actually we consider here, right? For shaded area, okay? So we're going to have that the volume of this new that actually you extend energy a little bit. The difference between these two could give you, if you do the Taylor series expansion, right, you will get this right here. And you, of course, can define this thing. So you will see that here, right? Okay. So next, so in the limit, actually this delta E approach to 0. So we have, so you must have this Okay, condition here, delta function. Okay. And of course, you must have this, right? Well, we're going to talk about this factor later. Well, and then actually it's going to be relevant in the quantum context. We should actually going to deal with that later. Okay. Any question up to here? Okay, then I move on. So let me recap you again for this situation with the isolated system. Right. So if you increase the energy, then the distribution going to be constant somehow. Yeah. So, to be constant, we should, but that constant depends on the energy as well. All right. So, oops, sorry. Seem like I just mixing up. Okay. Okay. Next, so we're going to look at equilibrium ensemble. Right. So at equilibrium, so we have a requirement that this rho must be constant, right? As I mentioned here before, right? So what does it mean? It means that this total derivative of the rho, I mean the time derivative with respect to the time must be 0. And also, I mean, no, not this one actually, because we already put this condition, this one, I mean the partial derivative, right, must be 0, right, and then you're left with only this Poisson bracket, right? And so if you have this equation, we knew that any quantity actually define on this phase state, right? any quantity that we find on phase space has 0. Boson bracket with the Hamiltonian right, that is constant, right? That quantity is the constant, right? That actually this is what we have from the context of the classical dynamics, right? You know that any quantity that actually, if you compute Poisson bracket with Hamiltonian, is going to constant with respect to the time. Right. It doesn't change with time. The system changed its microscopic scopic state. Actually, microstate, actually, to make it short, continuously right, even in equilibrium, but the distribution of microstate within the ensemble become independent. Okay, that is the message that actually we get from this equation. I'm going to draw you cartoon again. What does, okay, listen carefully before you make a note. The first sentence, have a look at the first sentence. The system change its microstate continuously, even in equilibrium. What does it mean by this sentence? What does it mean? You know?
It change its microstates. Even in the
Yes. So suppose that actually you have a box of gas, which is now at equilibrium. What do I mean by equilibrium? It means that the particle actually fully distribute. Okay. Okay. Throughout the box. Okay. But there might be this kind of state point, 0 point here, and so this bool state here at this time t0, at this time t. All right, and then you have, of course, that you have rho t, and later time you have a look again I might put the red here. And how many colors? I have the orange here, okay? And so later time, still your particle, I mean the state or the, your particle is still fully occupied the whole box. But the white dot might move to be here, and the blue dot might move be here, and the orange might be what? This here, and then of course the red, this is the red one, right? No, the pink one, anyway. You know what I mean? But this is still the same, I mean, which is actually, I mean, the distribution is still the same, but the configuration of each of the molecule might be, it might be not, it's not the same, right? But effectively, the distribution is still the same. That means that you get the distribution preserved, right? Is that clear? Okay. Okay, good. Xinครับ แต่ว่าอยากให้เสร็จตรงนี้ก่อนครับ ใจเย็นครับ หิวเหมือนกัน แต่ว่าเอาให้จบครับ so evolution okay, this is kind of definition of isolated system, right? There is no chain of internal energy, right? Microcanonical ensemble. Okay, and yeah. So the average value of any observable is given by this one. Of course, we have the we use the notion of ensemble average, right? Yeah, and this is a bit this is quite the advantage that actually if we claim actually your system is ergodic, then you can use the ensemble average instead of time average. And then you can, in practice, you can do the computation, right? That is the thing. But otherwise, then you have to wait until your system reaches to equilibrium, which actually might be a very long time. Something like that. Okay. And okay. Oops. Okay. This is the step function. Yeah. And so what you get is this one. Let me give you example and then we stop. Okay? And then in the next week we continue. Sorry about this. I just apologize to เป็นพิธีอะ Anyway, so let's look at the example. A classical gas. The ideal gas, actually, a classical ideal gas. To make it simple, and you have the Hamiltonian in this form, which is very simple, right here. So you can start to compute this quantity to make sure that this is isolated. To put to make to this to put actually this is an isolated system, right? So you're going to have Q actually Qn. This is Pn, and okay, this that you need to compute, okay, and bar is this one. So you're going to have the same here. So Iขี้เกียจอะ okay ครับ All right, so you have this step function, right? So it means now you have to deal with the integration with respect to the delta function and the step function, right? Okay. So let's look how to do it, how to deal with this. It's not difficult. So we look at this n-dimensional Gaussian integration. We have, it's very simple, right? And so if you look at in the spherical spherical polar coordinate, your I will be transformed to this. This part would involve all the angular parts of integration, but in the hyper dimension, right, is something which is actually, and so you can filter all right. Since the angular part doesn't involve anything with the integrand, right? You can take it out and then you change the variable, you get that factor 1/2. And so, and okay. So you will get 1/2. Yeah. And so I'm not going to give you a proof, but I give you a result. Actually, in this situation, you get this, right? And in the case that if you have D to be 1, it's going to give you exactly the same with that. Is that not right? I think so. No, you have to take this to be 1 and then just cut it, and then yeah, right. Yeah. If D to be 1, you get that exactly. Yeah. Okay. Oh dear. Okay. So next, we introduce the surface area of the unit sphere. So we shall call this quantity at the surface area, right, of the unit d-dimensional unit sphere. So this whole bit going to give you v to the power n, right? And so here you will get the condition that actually equal to 0, right? Pi. Then you get actually Ti here. Let's put this ignore the index, and then the total P is somehow proportional to the square root to ME, right? So you can change the variable, right, to this just one P, and then you can group this to be just one integration. So you will get v to the power n and 2me dp here 3n, and you know the answer, which is actually this give you factorial, hit this one. And then you can further simplify is a little bit more. Factorial, right? So this is going to be your omega bar, right? Once you get this, so at large n condition, n factorial can be approximate to be this. I believe that you know this formula, like stirring here. Okay, we almost there. I'm also need to get something into my stomach now, but well. So approximately 4 pi this is E 3n/2, 5n/2 here. And once you get this bar, you can compute this omega, right? Because you can do the derivative with respect to the t. So you will get 2 pi m e minus 1 and factorial. Again, at n very large, right? You will see that this can be approximate again by use this Stirling, right? And then you find okay, which is this one. Okay. And so let me see, because shall I continue or shall I stop here? Then I stop here, because next we're going to use this to compute like entropy, but in the context of the classical statistical mechanics. But I think today is a bit late and I stop here. And I hope you see the point, but we haven't finished this example yet. We're going to continue next class on the compute, the entropy. So if you have question or anything,